spokesperson. Okay, good people, good evening. This session is recorded. Welcome to our lesson session. Tonight we are doing a lesson 12. I would advise you to have your lesson open. Yes, miss?
Angazi noma mina, but the volume is quite low. Angazi noma mina, but mine is at its maximum.
Oh, low. Is okay. I'll come closer to the microphone. I was switching on the power. My power was low. Okay, I will come closer to the microphone, hoping that your volume will improve. How is it now? I'm closest to the microphone. Okay, I will start by sharing the Proteus presentation. Is it better? Okay. I'll start by sharing the Proteus presentation or the simulation. Then I will switch off the camera. I'll switch it on at the end also. So I'm sharing my Proteus now. I will first demonstrate what we are supposed to do. Can we all see the my Proteus presentation, the Proteus schematic? Let me enlarge a little bit. Okay. This is a simple circuit, good people. It consists of a potentiometer on the input side. This is we use this as a DC source. You click on this tool for the terminals, and we use that for our DC source. Then you can double click it to set your voltage. We want to work with 5 volt DC, so we select 5 there. Then on the output, we have 10 LEDs. Why 10 LEDs? We want to simulate the 10-bit analog to digital converter. So we want to take an analog input and represent it in binary using a 10-bit number. If you look at this, this will be the LSB and this will be the MSB. For the 10-bit, we then need 2 registers. In this example, I used register C and I took 2 pins on the register D. I will explain that as we go along. So normally, if we use a switch represents a digital input because it's on-off. You can switch it on and switch it off. We did mention that all the pins that have got AN on them, it can be used as analog inputs. So in this example, then I'm using RA0, which is AN0. That AN0 means RA0 can function as a channel 0, analog channel 0, or channel analog input channel 0. Okay. So therefore, we use a potentiometer here to supply a varying voltage. It can come closer to 0 here or go up towards a positive. As we read this now, it means in voltage, this will range between 0 volts and 5 volts. I'm supplying 5 volts there. When this is on maximum, I'll be sending 5 volts. When that is at minimum, I'll be sending 0 volts. Then I need to scale that 0 to 5 volts and display it here in binary. Some of you guys are doing process. In process, you use the similar, or you deal with what you call transducers. So for example, in process, you use a 4 to 20 milliamps. That is a current transducer. And you use a 0 to 5 volts as a transducer to represent the pressure and so on. There are so many transducers. So if it's supplying, if it's 0 here, it represents a certain value. If it is maximum, represent a certain value, and you scale in between. For us then, guys,
Sir,
Sorry,
you're
sir.
muted.
Ngithelile asibuzo.
Gatsheni awuzwakali ngapha.
Sir, I'm muting mic.
Close my mic. I did not close it, but I see it closed now. Do not interfere with the lesson, guys. Okay, my mic is open now. I hope you can hear me now. Okay, so look here, good people. I just turned on the switch or the power. This is almost at the middle. We have a display there. Let me run this to minimum. I don't know what voltage I selected there, but anyway, I don't know what resistance I mean. I did it. So we're going towards 0. I want to go to 0. So if this is on minimum, then we expect all LEDs to switch off or to be close to 0. Okay, look now. My pointer for this potentiometer is at is lowest. When it is lowest, I'm supplying ground there, which is 0, and all LEDs are off. So as I keep on increasing the resistance or the wiper between this and the ground, it forms some resistance. As that resistance forms there, it produces a certain voltage. And that voltage is a fraction or a percentage of 5 volts. Until when this arm is pointing at maximum there, I'll be sending 5 volts there. So what we are doing here, guys, we take this fraction of resistance that we have here and connect it, convert it to voltage, and display it as a digital output on the outside. So this system now, we call it the analog to digital inverter or converter. The microcontroller has got a built-in ADC circuit. For us then is to set it up so that you can be able to read the analog input. Okay, let's increase the resistance now. I'll click there once. You see this LED come on. This is LSB, that's MSB. So it's 1010. It means that is equivalent to 10 in decimal, 1010. Then I click. It depends on how much that takes a move. But all that I'm showing is that as I'm clicking, this is demonstrating an output in binary, and that value is increasing. We read from the bottom, and the MSB is at the bottom. So this is 11110110. You can work it out what it is in hexadecimal or in binary. So this will increase, keep on increasing until it's 11111 when it is the maximum. If then you want to build a circuit like this, especially when you read the sensors, you have to scale this so that you can be able to work out exactly what is the voltage or the reading at each point. That is what we will talk about at the beginning of our lesson. I just wanted to demonstrate it first. So when that reaches maximum, we expect all LEDs to turn on. Look now, we started with all LEDs off. Now they are all on. So when this wiper is at 0, we are sending 0 volts. This all the LEDs will be off. As this increases, we are at each instant where that is pointing on your potentiometer, you take that value and you convert it to binary and display it on that side. So until when that is maximum, we are sending 5 volts direct, because that is 5 volts is maximum, all LEDs will turn on. Now, the purpose of our study, we've got two objectives here. Firstly, we want to see that if we know the value here, for example, if I click this twice or several times, this sends a certain voltage here. The purpose of us is that if I know the voltage here at any instant in time, I must be able to work out what is the 10-bit binary number that this will produce. That's the first thing. Next, then we want to be able to set up this system such that it can be able to take up any value and convert it to binary or to digital and then display it. Before I say anything, guys, is there anybody that has a comment on this schematic? Are we okay?
Sorry, sir.
Yes.
Can I ask, sir?
Yes, go ahead.
Okay, sir. My question is that where do we like increase the resistance? I didn't.
Okay.
I missed the part.
Okay. Do you see this potentiometer here?
Yes.
You see my cursor?
Yes, I see it.
I've got 2 dots here. This is an active port so that it can simulate. If I click this dot above, it's increasing the resistance. If I click the dot below, it's decreasing the resistance. So what happens is that this wiper here is making contact with your resistor here, such that at any point in time, it's measuring the voltage is what is between the supply and your pin. So as it is here, we are connecting this in contact. So remember, if you look here, we've got 5 volts there, we've got ground here. So we've got current that is flowing in this voltage. And we said the potential difference is always between ground and the point. So as I'm clicking here, can you see if I'm clicking this top dot here? I am increasing the resistance now between this arm and the ground. So, but it's a small portion. When the resistance is small, this will produce a smaller number. When the resistance is maximum, that is equivalent to maximum voltage. So here we are actually converting resistance to voltage, whatever. We can take a potentiometer as a form of a transducer, because we are working on the resistance here, but we are controlling the voltage that we are supplying on this pin. With the digital input, we send 0 and 5 volts. But with this setup, with the voltage we are sending is the portion between this ground and that point here, the pointer. So if I click here, I am increasing the resistance. Can you see that? That is from clicking the one above. You see the number there is increasing. But if I'm clicking this dot that is at the bottom, I'm reducing the resistance. So the bottom dot is decreasing, the top dot is increasing. I think that is what you were asking.
Yes, thank you. Thank you very much, sir.
Okay. Then now, guys, before we go on that side, look here now. We have a 10-bit. This 10-bit, we connect this all of port C and the 2-bit in port D. If we like, we're going to connect all of port D and the 2-bit on port C. It depends on how we want to work on it. That is what I will explain on the other side. If nobody has a question on the simulation, then guys, allow me to first show you the program. I realized that I did not give you the program in the lesson, but I will either email it to you or we can discuss it in class and give it to you. So this is a simple program. Let me reduce this window so that we can see more of the program. It cannot be smaller than that, okay? I wrote this program on Friday, last week, Friday the 6th. Okay, so we are familiar with this. We use our header file, then we are going to use a delay. I just called this delay, not MS delay. And the main program is void main void. We said here we can write a void or we can leave these brackets empty. We are displaying on port C and port D, although we are using only 2 pins on port D for now, but there's nothing that can be wrong if we change and use all of port D and 2 pins on port C. So I made port C and port D the output. The potentiometer is connected on RA0. Then I said the trace A bit dot the trace A0 is equal to 1. That is, I'm assigning 1 there. If I like, I can define that there and give it a name, maybe say port. So guys, please, I've noticed this with many. If we use the trace, we write the full word. We do not write RA. But if we use the port, we can say port A bits dot RA0. But if it is a trace, we must always say trace A bit dot trace A0. If it's a trace, you write the full word, because the R is the abbreviation for the port register, not the trace. Please don't confuse that. So we make RA0 an input. Now I put 81 on ADCON 0 and CE on ADCON 1. Now guys, we have used ADCON 0 with you. So today then we'll get a better opportunity to look and see why do we give you that instruction. For all other operations, we set 07 there. But today I'm using 81. So in the theory, then I will be showing you why we use 81 and why we use port CE there. That is in the program. Then guys, for test and for exam purposes, you must be able to set up the ADCON registers, analog to digital conversion control registers. So I've got ADCON 0 and ADCON 1. Okay, then this is what is happening in the program. Here, I started with a delay of 1 cycle. Then this ADCON 0 bit.go, that is a start to start the conversion. I will show you that when we look at the ADCON register. So we put a 1 on this bit so to start the conversion. Guys, this while some of you have practiced with that. This, if you say while, you mean wait when this go done bit is 1. So this is the same bit there. This is a go done bit. You say when this bit is still 1 wait. In other words, nothing will happen until this bit changes to 0. This is how the ADCON works then, guys. I put a 1 there to start the conversion. And this bit will remain a 1. And when it has finished the conversion, when it has finished, depending on how long it takes to convert your number, we'll look at the conversion time now. When it has finished the conversion and the result is available, this bit will become a 0. So in your program then, you put a 1 there and wait for this bit to become a 0. When this bit becomes a 0, it means the converter has been able to convert your value to digital and the result is available. Since it's 10-bit, we combine 2 registers then to hold the result. Remember, we're working with the 8-bit system. So we then use 2 registers. One is the address register low byte. We call it ADRES, address result low byte, which is the AD result. That ADRES is analog to digital conversion result register low byte. This ADRES H is analog to digital conversion result register high byte. So I've got a low byte and a high byte. In the example that we had in our schematic, we're putting the low byte in port C and the high byte in port D. But our high byte in that case consisted of only 2 bits. So this program then, guys, is the program that does what we were seeing here. What we see here then is produced by that program. So I will explain the principle of analog to digital conversion in detail. Then we can come back to this schematic and this program, then hoping that we'll be having some understanding. Guys, allow me now to share the lesson. Together with the lesson, then I'll also like to share the data sheet so that I can show you these things on the data sheet as well.
Before you share, can you please go back to the source code? I have one question.
Okay, let us look at the code before we share. Where is it?
On the source code.
Okay. Okay, here it is. Can you still see the schematic code, people who haven't changed? Can you see the code now?
Yes.
Okay. All right.
So my question is right after you delay once, then you said it an add-con bit go. Then that sentence
on this line, the line that is highlighted.
Yes, but
okay.
The one that is below or ahead,
this one.
Yes, that one.
Yeah,
I think it will be having mthelela on the second one.
Yes. So if you this one, if I put a 1, this is the same bit, ADCON 0 bits dot go is the same bit as ADCON bits dot done. This bit, when it is active, it means the register, you start the conversion. If it is 0, it means the conversion is complete. So we call it a go done bit. Done means completed. Go means start the conversion, and done means the conversion is complete. So what I do, I put a 1 on this bit to start the conversion. When the conversion is complete, this bit will automatically become a 0. So with this line, this while, I'm waiting for that bit to become a 0 to show that the conversion is complete. When the conversion is complete, it means the results now are available in my result holding registers, which is AD-RES-L and AD-RES-H.
Yeah, I think
it's are you okay with that?
Yes, now I can.
We can revisit it again, guys. Okay, let me share the lesson. I'll start by the lesson. Then we will look at the data sheet. Then I'll give you a chance, guys, to ask questions. Now, good people, I am sharing the lesson. And I would advise you to have your lesson open with you. Can you see the lesson on my screen first? Are you still with me?
Yes.
Yes.
Yeah. Okay. Now, guys, I said to you in the beginning, I will send you the lesson beforehand and expect you to read it before you come to class so that when I explain, you have an idea of what we're talking about and it will be easy to understand. In this lesson, I said, read chapter 8 in the notes. I know nobody has checked that chapter 8. And I said, read section 13.1 and 13.2 in the book. I know nobody has read that, those sections. Maybe, guys, I'm not giving you sufficient credit. Let's assume that you only checked chapter 8 in the notes, and you checked 13.1 and 13.2 in the book, and you checked chapter 20 in the data sheet. So I'm not going to look at the notes, guys, I gave you. I'm not going to look at this. The book is giving you all the theory that I'm going to discuss with you. But I will share chapter 20 with you in the data sheet to just show you the registers. but I've got the registers here in the lesson. Then in terms of theory, we say the PIC 18F458, our microcontroller has got 8 analog channels. We do have microcontrollers that have got up to 16, like the 8722 has got 16 analog channels. This one has got 8. So these, forgive me, good people, I said AN0 to AN0, it must be AN0 to AN7. It must be AN0 to AN7, not to AN0 again. It must go up to AN7. They run from AN0 to AN7. I will make the correction for that. Then we say a sampled signal is converted to a 10-bit number. As I was changing the wiper on the port, each time there it takes as if we are sampling the voltage on your resistor, and you send a value on the input pin, which is in this case it was AN0 that we're using. And that value now, whatever the voltage, is converted to a 10-bit binary number, and I was using LEDs to display that number. But for you, now we've done the LCD. There's nothing wrong that can stop you displaying on the LCD. I remember there's a group that I had some time ago that I asked to display, but you were using assembly language to display on the LCD instead of on the LED. It was their assignment. As I gave you guys an easier assignment. I gave the others to do this circuit and then display on the LCD, but they did very well. Okay, then we say here, the number of bits in a digital number, in this case, this 10, we use n then to represent the number of bits. So this n then we call the resolution of the converter. If n is small, the output is not very clear. Not very accurate. Let me say clear, it's not very accurate. If this n is big, for example, guys, we can work with an 8-bit number. If it is 8-bit, it will not be as accurate as a 10-bit. If I use 12-bit, it will be more accurate than 10-bit. If I use 14-bit and so on. As you increase the number of bits, we are increasing the resolution and we are increasing the accuracy. For us, then we will work with a 10-bit number. So our n will be 10. We say then the ADC works with the reference voltage Vref. So, guys, I request that anyway, it was page 4 on the notes, I think. We will look at that. There are 2 pins, that is, one is Vref plus and the other one is Vref minus. We can work with a positive Vref and a negative Vref, or a positive Vref or a negative Vref, or work with a Vref and ground. Or we can use VDD. If the Vref is not specified, we assume that we are working with the supply voltage VDD. In other words, we can change the input. Instead of being 0 to 5 volts, it can be 0 to any value depending on what we supply here as a reference voltage. Also, we can be able to produce a bipolar signal by having a negative reference and a positive reference, like if you sketch a sine wave. So we can be able to monitor a sine wave with our signal, get the reading from the sine wave, store them, and we can be able to reproduce that sine wave. So the output voltage that we apply as a reference, we call Vref. And our Vref can be VDD. If it is not specified, like in the example that I gave you, we did not specify any Vref, so we're working with the supply voltage, which is the VDD. Now, we take this the supply voltage, and you divide it by into a number of lines depending on the number of bits. That then give you the size of each step, or as you change from one, as I was clicking on the resistor there, taking one step at a time. This will tell you how much is each step of your voltage. So the step size then is given by taking your Vref and divided by 2 to power n. So this step depends on the number of bits you have. We said the n, small letter n here, is the number of bits that you have. So that it gives it each size, means you take your signal and you can divide it into a number of lines, so that if your reading is pointing at a certain line, you can estimate the voltage or the reading to that line. Then this is what it is the step size that we have. We take this now and compare the input that we are having. But what do we get on the output that we call the digital output, D out? This V in then is the voltage at the pin. As you change your analog input, we are applying a certain voltage on your pin as input. If you take your voltage, your pin, and you divide it by this step size now, you will get a value. Then convert that value to binary. It will give you the equivalent of the digital number that you have. Let's look at this example quickly, good people. Then I'll give you a chance to ask questions. So this is the schematic that I just displayed to you in Proteus. Here, I just put 10 bits output and set LSB to MSB. So sorry, but in Proteus we were specific. I showed you port C and port D. So this is the potentiometer. We are swinging the input here. As we move this now, we are changing the V in, the voltage that we are applying on the pin. As we get that, we use the analog to digital conversion here to display the binary equivalent. So now be careful that here we are displaying a 10-bit number, but we are working with the 8-bit system. That will come to practice very soon. Okay. Now, how do we get the value? Here we say if Vref is not given, we use VDT, which is 5 volts. This is a 10-bit ADC, so N is 10. We said the step size is Vref over 2 to power N. I'll request you guys to practice this calculation so that you don't do it for the first time in the test or in the examination. So you take your Vref, which is that one, and you divide by 2 to power N, which is 2 to power 10. Guys, 2 to power N is a kilo. I hope you did that either in digits 1 and digits 2 or in programming. You speak of kilobits and kilobyte and so on. In a digital setting, guys, a kilo is not 1,000. A kilo is not 1,000, but a kilo is 2 to power 10, which is 1024. If you speak of so many kilobyte bits, then don't think of 1,000. Take a 1024 multiplied by that value to find the exact number of bits. So if we take 5 volts then and divide it by 2 to power 10, it gives us 4.88 millivolts. That means each step in between 0 and 5 volts is 4.88 millivolts. Then this now depends on where I'm pointing here, how many steps I take up there to get my V in. We take that value and we convert. We set now to convert to say D out is the V in, the voltage that we supply in there, divided by the step size. In this example set, find the 10-bit digital number when the input is 4.25 volts. That means I'm swinging this up to the point where it is close to 5 and is sending 4.25 here. The question is, what will be the binary number? Okay. Then we set V in over step size 4.25 divided by 4.88. That gives us 871. If you take this 871 and convert it to binary, it gives you 110110011111. That is a 10-bit number. So that means if I could shift this to that, these are the LEDs that we're going to turn on my LSP. Guys, this is a theoretical calculation and you must be able to calculate this. Is there anybody that has a question on this section so far before we go to the hardware setting? Anybody having a question so far before we go to the hardware setting? Yeah, Naikoluma. Okay, let's assume that you are all okay then, guys. Let me switch off the camera. If you encounter any difficulty, then don't hesitate to let me know. We will revisit that. Now, yes, yes.
Okay, cela ukubuza kuqala uV-in utest uthathaphi?
Okay. Now, here we have a potentiometer. This potentiometer, we are changing the resistance between ground and 5 volts. As you swing this here, you are supplying a voltage here. So this V-in is the voltage that we have between the ground and the supply or this wiper. So as you see that I had two dots, I was clicking that. As I was clicking that dot, I was changing the voltage that I'm applying here. So V-in is what is the voltage at any point in time here. As I move this pointer here, I'm changing the resistance between the ground and the 5 volts. That resistance is proportional to the voltage. So that voltage at that time we call V-in is what is the voltage that we are applying to the microcontroller pin. That is V-in. So we change the setting of the potentiometer. When we change the at any instant in time, this is the reading a voltage from the resistor and sending it to the pin, and we call it V-in on the pin. I don't know whether you answered that one.
Ngiyabonga sir.
Yes, there was another question. Thanks for that, Nene. Nenhlanhla. There was another question, good people.
Yes, sir. How do we move like 871 to a binary, sir? I don't understand how do we get that number.
That must be your S1 and your S2 work. How to convert a number to binary. But guys,
It is right.
is easy. For you guys, you don't need to do that division and the what we call the remainder and so on and so on. You have scientific calculators. You just punch in a calculator and convert it from decimal to hexadecimal or decimal to digital. Here, I don't want to see the steps that you use there. You can use a calculator. Are you okay with that?
Yes, sir.
Okay, sure.
Oh.
Now then, guys, how do we set up the hardware to be able to do this for us? Now, this is what you need to know. We say the analog to digital conversion sequence. Now, this is explained in the notes. We say the 10-bit result is held in an analog to digital result high byte register and analog to digital result low byte register. We combine two registers. One is at why? Because we are working with the 8-bit system, but we are producing a 10-bit number. So we'll combine two registers and then we call one the address the analog to digital result register low byte and the analog to digital result register high byte. So we combine those two. Then we have got analog to digital conversion control registers. we've got AD-Con1 and AD-Con2. Guys, for each microcontroller, there are various AD-Con registers, and the structure is not the same. So if you work with any microcontroller, if you work with this one, it's okay, you can use information I'm giving you here. But if you work with another microcontroller, you must go to the datasheet and check where the analog to digital conversion takes place and find the exact layout of the register. I will take you to the datasheet, but for now, guys, this is the layout of the AD-Con0 register, AD-Con0, the analog to digital control register 0. Guys, you do not need to know this register off by heart. In the test and in the examination, I will give you this register. As it is, I'll give you this as it is at the back of the question paper. I will give you that. Now, you need to be able to interpret this. So the interpretation, guys, is given in the data sheet, but if you have your notebook with you, I would request you to write the explanation that I'm going to give you here. Starting from the MSB, this ADCS is the analog to digital conversion or clock source, analog to digital converter clock source. So we've got ADCS0, ADCS1, and ADCS2. ADCS2 is in AD-Con1 register, I will show. So it means we cannot work with ADCS0 and ADCS1 in isolation. We need to see what is ADCS2 in AD-Con1 register. I'll talk about that now. And these are the channel. We said this microcontroller has got 8 analog to digital channel. For 8 channels, then we use 3-bit. It means we can move from 0, 0, 0 up to 1, 1, 1, 1. So CHS, this is in CHS0, CHS1, CHS2. That is a channel selection bit. So all that you do, guys, to set up, I will come to now. If you want to set up any channel, you just put a binary number of your channel here. If you want AN0, you put 0, 0, 0 there. If you want AN1, you put 0, 0, 1. If you want AN2, 0, 1, 0, and so on. To choose which channel you want, you just put the binary number of the channel in these channel selection bits. Do you guys get that? Where's Wagan?
No.
Yes.
I'm saying you have to
So
select
in
which
the
channel we are using.
No, sir.
We have to select which channel we are using. For example, in the
We are muted, sir.
I can't see you, sir.
okay, sorry about that. Okay, I'm saying then, good people, that to choose any channel, for example, here, I'm using AN0. We said here we are using AN0. Then I must come here now. In this channel selection bit, I put the binary value for 0, which is 0, 0, 0. If here, for example, I chose AN5, I'm just making an example, then I must come here and put 5 in binary, which is 1, 0, 1. So to choose the channel, you just write a binary value of your channel on these 3 bits here. If it is 8-bit, if it's a 16-bit, there will be 4 of these. They will run from CHS0 to CHS3. In this case, there are 8, so CHS0 to CHS2. We start from 0, 0, 0, 0, 0, 1 up to 1, 1, 1, which is AN7. Then guys, also note here, I did explain this to you in the past that if on each bit we put R/W-a number, that means you can read the bit and you can write on the bit, and this tells you what it is before your program starts running. So that means all these bits are 0, 0, 0, 0. Then this bit in this microcontroller is not used and is taken as 0. If you look at this one, this is a go done bit. Is normally at 0. If it is 0, remember it's active low. That done there, it means active low. In other words, if this bit is 0, this is what is happening. If this bit is 1, that is what is happening. So if I put a 1 here, this will start the conversion. When the conversion is complete, this bit will become a 1. So here, look, done is active low. It means if everything is finished, this bit will be 0 to show that it is done. So we can then say AD 0, 012, or we can say AD 0, go if you wanted this, or comma done if you want this. We can call a go done bit. You can use the number set to start counting from 0, 0, 1, 2, or we can write what is in there, as long as we included that 18F458, then it will understand what we mean. So this bit then, guys, is for switching on the AD con. Guys, the AD con is there in a microcontroller. But look, this bit is 0. It means because the AD con, guys, it takes a lot of current, it is always switched off. If then you want to do analog to digital conversion, you start by putting a 1 on this bit to show that you want to do analog to digital conversion. Then you set up your channels. Then you set up the clock source, so clock speed, ATCS. That's the conversion speed. So, but this ATCS, guys, I said that it works with ATCS2, which is an AD con 1. Look at this register now, AD con 1. Here we've got ATCS2. So ATCS2, ATCS1, and ATCS0, the values that you put there gives you the conversion speed. That tells you how fast is the microcontroller going to do your conversion. You can control that. But by default, this is 0, 0, 0. I'll show you now what 0, 0, 0 means. I hope we are writing notes somewhere. This ADFM is the analog to digital conversion format. By format, we mean that you want your number now, your output, in AD-RES registers. You want it to be right justified or left justified. You want the number to start from left to right or to start from right to left. So if this is 0, that is a left justified. If this is 1, that is right justified. I will explain, I'll show you that now when we finish there. Then these are the port configuration bits. These are the bits now that set up your pins as analog or digital. These are the pins that set up your pins to be analog or digital. We call them the PCFG or the port configuration bit. You can make a recombination of that. Now look here. This is 0, 0, 0, 0. That means all the PCFG bits are 0. What does that mean? Let's look at this table. Guys, this table will also be given to you. Look here, PCFG, if it is 0, 0, 0, 0, AN7 is analog, AN6 is analog, AN5 is analog, AN4 is analog. So they are all analog. That is why we said we must be careful if we are going to use a pin with AN, because by default, if you don't set anything up, the PCFGs are all zeros, making all your pins analog. We said for our application, we put 7 on ADCON 1. Let us look at what is 0, 1, 1. This is that. You see, if you put 0, 1, 1, actually 0, 1, 1, that bit can be anything, but we make it a 1. We always put 0x07 on ADCON 1. By so doing, we are making all pins digital. We are making all pins digital. So if you put 07 on ADCON 1, we are changing all pins to digital. Please get note of that. But what is the code that we can put on ADCON? Firstly, it depends on the channel that you are using as your analog input, and also depend on the reference voltage that you are using. So this combination here, this setting here of ADCON depends on the channel that you are using and the voltage reference. For example, if you want to use the AN0 with a positive and negative reference, you put 1111 on PCFG. But if you want to use channel AN0 only with the VDD and NOR, guys, VREF connects to AN3, VREF plus, VREF minus connected to AN2. So if you use VREF, then you cannot use AN pin, AN3 and AN2 as analog input, because that is where you put in your references. But if you are not using VREF, using VDD and VSS, like in the example that I gave you, we put 1110 in our PCFG. Now, before I give you guys a chance to ask, let us look at the program that I gave you. I said we put 0x81, am I right? It was 81 on the ADCON 0. Do you still recall that? Nisakon?
Yes, yes, yes.
So, what is 8? Okay, guys, so that you are with me, let's quickly go open the program again. Let me unshare this. I will quickly share the program. Oh, no, don't have to go there. I think I have the program. Oh, I didn't put it on this one. This one, I wanted you guys to work out the program, but I decided to give it to you again. I will give it to you. Let me unshare this, good people, then open the schematic, and then show you that program again. And I request you to record these values. I'm sharing the program again now. Please write these values down. On ADCON 0, we put 0x81. On ADCON 1, we put 0xC1. I want now to explain to you what this means. For test and for exam purposes, guys, I can tell you that set up the ADCON to function with this specification. Then you work out your values. Or I can tell you that I put a 0x81 on ADCON 0 and CAE on ADCON 1. What does that mean? So I can give you this and ask you to explain it. Or I can give you the explanation and ask you to work out this code. For now, guys, I request that you take out these numbers. It's 81 on ADCON 0 and CE on ADCON 1. I will unshare this and then share that the lesson again. Assuming that you guys have your lesson with you. Okay, I'm sharing the lesson again now. Okay, let us look at this. We set 81 on ADCON 0. 8 means 1. Let me write this here with you so that you can see. 8
Yes,
is
sir.
1. Let me change the color. Can I change the color of the typewriter here?
Yes.
It will waste my time, but you can see this. I will adjust it later. So it's 1, 0, 0, 0. That is 8, eh? We said, sorry, 0. We put 8, 1, eh? 1 is 0, 0, 0,
1.
1. That is what we are doing, eh? Now, let's not talk about this ADS. We said ADCS0 and ADCS1 work together with this one. We'll look at that. But look at what we have here. By putting 8, 1, we put 0, 0, 0 on channel selected selection bits. That means we are selecting AN0 as our channel. That's what I meant when I said you put the binary number there. So this 0 that we put here, we mean we do not want the conversion to start. Then this bit is not used, it's taken as 0. Where do we get that? We find it from there. Then this one now, we are switching on the AD converter. It means we want it to be able to do the conversion for us. But we need to set AD 0 or AD 1 again. We set on AD 1, what do we put? What number did we put on AD 1?
CE.
CE, eh?
0.
C
Yes.
is 1,
CE.
1, 0, 0. That is C, eh? E is 1,
1,
1, 1,
1, 0.
0. Am I right?
Yes.
So we are just putting what we got from the table there. Now, we say these bits are not used. These bits are not used, so we take them as 0. This ADFM means write justify. If we put 1 here, we mean the number in the 8-bit register must be right justified. In other words, we must start with the LSB from right to left. I will explain that later. So this one means right justify. So for this clock source now, or conversion source, we use 110. We will look at the ADCS table just now to see what that means. So this PCFG now we put 1110. Let us come down here and have a look. Here is our PCFG 1110. 1110, we are making AN0 an analog input, and we use VDD as a plus reference and VSS as minus reference. Do you see that, guys? Again,
No, sir.
No, sir. We don't see
No.
0, 1, 1,
Guys,
1. 1, 1, 1, 0. 1, 1,
We are
0.
lost.
Where is the forest?
In the
Okay.
bush.
Let's start from the beginning. I'll start here. Are you with me? Please pay careful
Yes.
attention. Pay careful attention. I gave you a demo using Proteus. In my demo, I connected my analog input on AN0. Then I displayed on port C and port D, but port C was my LSB, so I write justified so that all bits are on port C and only 2 MSBs are on port D. That is right justification. But where did I get all that? That now I came here to check in my channel. if your ADCON registers, now you need to know the control registers, plus the ADCS. I'll show you the ADCS now. I did not include the ADCS here, but we will look at it on the data sheet. Then I will modify this lesson. I'll put it on there. So here, this is the ADCON 0 register. I'm saying that you do not need to know this register off by heart. In the test and in the exam, I will give it to you. But you are required to know how to set it up. And this is how you set it up. The ADCS0, ADCS1 work together with ADCS2, that is ADCON1. So we not worry about them for now. We'll look at that just now. Then CHS, those are the channel selection bit. You select which channel you want to use here. And here you select which channel you want to use. If you want to, and I said to you, you just put the binary number of the channel that you want to use. If you want AN0, you just write 0 in binary as a 3-bit number because we are having 8 channels. So we work with 3-bit, counting from 0 to 7. If you want AN1, then you'll put 001. You want AN2, you put 010, and so on. You just put a binary number of the channel you want here. Then we put a 0 here so that the conversion does not start. This is a go done bit. So we don't want the conversion to start before we finish the setting up. This bit is not used, so we take it as 0. And this is an enabling bit. We put a 1 here to switch on the AD converter to tell the microcontroller that now we want to use the ADCON. The ADCON is always there, but it is not functioning. This bit is a 0 because it takes a lot of current, is not used. So I put a 1 here. Now, to set this up, in the program that I gave you, we set 8-1 on ADCON 0, and this is 8-1. Now, if we interpret what that 8-1 means, we said we'll talk about this, but we put 3 zeros on CH, it means we select AN0. We don't want the conversion to start, and we're enabling the ADCON. We are turning on the ADCON. Then we come to ADCON 1. ADCON 1 has got the justification bit. This is for the result whether, because we have got a 16-bit number, whether you want to start writing your number from left to right or from right to left. I will explain that maybe before. So either you right to justify the number or you left to justify the number. A 1 on ADFM is right justification. A 0 on ADFM is left justification. If you say right justification, you mean that we start by filling up the address low byte register. If we left justify, we start by filling up the high byte. We will discuss that in finer details as we study further. Then we said we put CE in the ADCON 1. CE is 1100. So now I'm telling you this one means we right justify the result. We will discuss this one together with the ADCS1 and ADCS0. These 2 bits are not used. Then the last 4 bit, this E is 1110. That is the port configuration. Your port configuration now, guys, sets up your analog pin to which channel you want and whether you want the voltage reference to be the supply voltage or external voltage, positive reference and negative reference. That is what we set on the PCFG. You can write down there that PCFG means port configuration. Okay, now in our example, we put 111. Then we come here and look what that means. What that means. So this is a 1110. 1110 means all the unused channels are digital. but AN0 is analog. In our example, I used AN0. So AN0 is analog. Further to that, if we use 1110, we use VDD as positive reference and use the supply ground as negative reference. So there is no external value. In other words, we are working with 0 to 5. This is what was given in your example there. Now, you can therefore change this PCFG depending on whether you want to have positive reference and negative reference and which channels you want. You can have more than one channel as analog and you can have more than one channel as digital. It always depends on what you want. For example, if I put 0001, it means I'm using all channels as analog, but I'm having a positive ref, VREF, but there is no negative reference. So in other words, your voltage will swing between 0 and the maximum that you are applying on your VREF. For our example here, our voltage swings between 0 and 5. But if I put 0001, then it means I'm supplying a positive voltage. If my positive voltage is 10 volts, it means I can convert between 0 and 10 volts. That is giving me a wider range. If I take 0010, it means AN5, AN6, and AN7 are digital, but all these other pins are analog. And I'm also using VREF, positive VREF, and I don't have negative VREF. Guys, VREF is connected, positive VREF is connected on channel AN3, which is RA3 in simple terms. It connects the VREF. Then if we use it as VREF, then we cannot use it as an analog input. Now, let's look at this example here, 10000. So I have positive reference and negative reference. That means now my voltage can swing between a negative value and a positive value. Maybe I can connect minus 10 and plus 10, or minus 5 and plus 5, depending on what I want. Say minus 10 to plus 10. So I can swing those values. But now I'm using AN3 and AN2 for reference. Then these pins are not used as analog channels now. And I only have AN0, AN1, and the AN4. So these are the channels that I can use for that. So this combination, guys, shows you what you can get if you make any combination. But this combination depends on what you want to do and your specification. If the specification says nothing about the external reference voltage, then you assume you are using VDD. But if we are given the positive ref, then you choose the channel that will have your positive ref. If you are given a negative ref, we do have a situation where we only have a negative ref and not a positive ref. In other microcontrollers, it looks like this microcontroller does not want us to operate with a negative voltage. We do not have a situation where we only have a negative ref and no positive ref. So we can swing between a negative number and a positive number. This then we call the port configuration. Again, guys, for test and for exam purposes, I will give you this table. Yours is to be able to set it up. After you set this table up, then you can go and write your program. When writing your program now, from these tables, you find the values that you put there. Once you have your values that you put there, guys, all that you do, you just put a 1 in this bit. Then in your program, you wait for that bit to become a 0. When this bit becomes a 0, then you go and read your AD-RES registers. If you guys not have questions with this, then I will share the data sheet and show you this plus all the other information that is missing. Is there anybody that has a question on these tables before I move to the data sheet? Anyway, these tables are there on the data sheet again. Just allow me to unshare this. Then I'll share the data sheet. Then you can still have access to those tables. Now I'm opening the data sheet. Okay, Let me share the data sheet now. Okay, let me try and enlarge that a little bit. Let me see if I can move this up. Okay, I'll move it to 100%. Okay, that is a bit better. We can be able to see that. But guys, you were given the data sheet. I'd advise you to look at it. Oh, okay, so this is the layout. Oh, if I click here, it changes the settings. I must say, I think if I select the hand, it will stop with the changes. Okay, well, the head is selected, but why? Oh, I don't know why it's changing, guys. Well, we want to worry.
Say, are you there? Say, your mic is muted.
So sorry, good people. I muted my mic. I was attending to something. I will try not to click here because it changes the setting. This is a chapter 20. We said chapter 20. This gives you all the explanation, guys. I'm not going to go through that. I want you to read that. But here, this is where they explain all the bits. I will just quickly show you what we're talking about. Please do read that. So this is the conversion time and all that. We are not going to go into details and doing all these calculations, guys, outside our scope for now. But if you design something that has an ATC, then you'll need to know that. So a few semesters back, I had students that were doing design project and they were using a temperature sensor. They worked with this and I had to assist them with that, okay? Now, this is the configuration that we want. So all these are the specifications and all of that. So they give you all the theory that you need here, guys. What I was summarizing for you. So all of this. These are the registers that are associated with the AD conversion. I want us to go to specific to what we want. CMCon. Oh no, so this is no comparator. So maybe I should have gone up instead of going down. So the CMCon is also explained just below that, the comparator. For us, we are looking at the AD con, not on the CMCon. So 20.4. Okay, so they start with the registers and the explanation at the bottom. Okay, let's quickly look at this now. Now, I want to, let's look at this ADCS. This is ADCS. For us, guys, we put 0, 1, 0. Am I right? It was no, it was 1, 1, 0. 1, 1, 0 is the same. So is the frequency of the oscillator divided by 4 or by 64. It means we're running faster than the normal. Normally, we work with the frequency of the oscillator divided by 4. That is the operation of our microcontroller. But for this, we put 110 on ADCS. Our ADCS was a 110. That 110, it means we wanted this to operate faster. You can work out the frequency of the oscillator divided by 4. How fast is that going to be? I haven't worked that out, but it will produce the result very quicker. That's why it was responding with a click there. Okay. Then here is the AD con 0. Here is AD con 0. And here they explain here. So the ATCS, this is a ATCS2 is on ATCon1, ATCS0 and CS1 and NTCon0. These give you the ratio of your oscillator to tell you how fast it can be able to produce the result. If it is over 4, it means it's working on the speed of the microcontroller with a 4 megahertz crystal. But if it's over 2, it means it's working at a slower, it takes longer time, same thing like this. As you increase this number, it is operating faster. Then here, bit 5 to 3, those are your CHS bit, CHS0 to CHS2. So here, 000 means you are selecting AN0. 001 means AN1. 010 AN2. That is what I meant to you when I said you just take the binary number of the channel that you want and you put it on this bit, CHS0 to CHS2. Can you see that, good people? Then the go done bit, this says if that bit is 1, AD conversion is in progress. You are starting the conversion. If that bit is 0, it means the AD conversion is not in progress. In other words, conversion is complete. So you put a 1 there. When the conversion is complete, that bit will automatically become a 0. So in a program, after you have set up all your bits, you just put a 1 there and wait for that bit to become a 0. That is your AD con 0. Then your AD con 1 here, we say ADFM. If it is 1, that is right justified. If it is 0, that is left justified. So we put 1 on ADFM there, and that we are right justifying. Now we've got AD res H and AD res L. Guys, is there anything else that you'd like me to explain? We have explained the ATCS, and we have explained this PCFG to you. Maybe I can try to explain that right justification for you. Is there any question before we talk about the right justification, guys? We have come to the end of our lesson.
Sir, can I ask you, but not on this lesson?
Yes.
Can I ask something?
Wait, allow me then to
chapter?
conclude this lesson because we have come to the end. Then I'll give you the time to ask about anything else.
Okay.
Please write that question down because we have come to the end. I want to conclude this. Is there anybody that has a question on this lesson before we conclude? Then we go open. Okay, guys, in that case, then good people, allow me to stop the recording. Then we will talk about general questions and anything else. Okay,